Okay, well, so I'm going to be introducing Jim, but first I wanted to say that we will be taking Jim for lunch today. We can plan on departing here from the door at 2 p.m. We're going to La Noria if anybody wants to join. We have 2 cars, no, so we can fit some people. So you're welcome to join us for lunch with Jim. And well, it's my pleasure to introduce Jim Jackson. Actually, Jim and I have known each other for quite a long time already, more than 10 years. When he was kind enough to invite me to the Sofia headquarters, and I had the opportunity to meet the people there and give a talk. But then we realized we had quite a number of common ideas. And so it's a pleasure to have him back. And maybe now we can work something.
Yes.
And Jim got his bachelor's at Penn State and then his PhD at MIT. Did postdocs with Jack Welch at Berkeley and Reinhard Genzel at the Max Planck. Then he spent 25 years at Boston University as professor there. And he was department chair and associate dean for research. He was the head of school at the University of Newcastle, Australia, so he moved to Australia at some point. He's been associate director at Sofia, director of the Green Bank Observatory, and now he's happily retired. He says that he's enjoying the pleasure of being able to do research with no interruptions, no administrative interruptions. So, very welcome, Jim.
Great, thank you, Enrique. It's a real pleasure to be here, and I must say I'm eating way too much good Mexican food. I really like it, really enjoy it. So I'm going to talk to you today about ammonia hyperfine anomalies. And this is a problem I've worked on for 43 years. So one of the nice things about retirement is you can get back to old problems and apply new techniques. Computers are a lot better than they were 43 years ago. The canned packages that you can find are a lot better. And we've come a long way in our understanding. And I think we are starting to understand this problem, and it only took me 4 decades. All right, so ammonia is the best of all possible molecules. It is my favorite molecule because it's so versatile. There's a number of things that you can do with ammonia that you can't do with other molecular lines. It's fairly abundant. It traces dense gas. And there are a number of transitions that are right around 24 gigahertz. They're all roughly the same frequency, not quite, but close. And so with the same telescope, you can observe many, many ammonia lines simultaneously. Now, these energy levels for these transitions are quite varied. And it's because there are very different energy levels, you can use the Boltzmann equation to deduce the temperature from the relative ratios of these inversion lines. So, for instance, here in red, you see the 1,1 ammonia line toward this little star-forming core. And then in green, you see the 2,2 ammonia line. If the gas is very cold, the 2,2 is faint relative to 1,1. If the gas is very warm, the 2,2 is bright relative to 1,1. So those line ratios give you a temperature. Ammonia is an excellent thermometer. The other thing that happens is you see these 5 hyperfine lines. Now, this is the subject of my talk. These lines are brought about because nitrogen is a football-shaped thing rather than American football, sorry. Oblong thing rather than a spherical thing. And because it has a quadrupole moment, it interacts with the gradient of the electric field in the molecule and it splits the line into these 5 hyperfine lines. Now, what's nice about these lines is the relative ratio of the hyperfine lines to the main line tells you how much opacity you have. It's an optical depth meter. So it is a pretty versatile molecule. By mapping simultaneously a few of these lines, you can deduce the intensity, the temperature, the optical depth, and the velocity field in one set of observations. So there's a lot of information contained in the ammonia spectrum. Now let's talk about these pesky hyperfine lines. So this is, as I said, it's a nuclear quadrupole interaction. It splits the line into 5. And I can never remember the quantum numbers, so I call them left outer, left inner, main, right inner, and right outer. All right? Those are the quantum numbers. If you want to memorize them, feel free. They're there.
Now, what's in the optically thin LTE case, that is, everything is at the same excitation temperature, the hyperfine lines have a specified ratio to the main line. So in the optically thin case, the outer satellites are 22% of the main line, and the inner satellites are 28% of the main line. And this is an optically thin theoretical spectrum. If you increase the optical depth, the hyperfine lines grow relative to the main line, but still you get the same brightnesses for the outer satellites and the inner satellites. The right outer to left outer intensity ratio, which I'm going to call rho low, is 1, and the left inner to right inner satellite ratio, which I'm going to call IRyA, is 1 as well. Okay? And this is true in LTE. So what do we actually see? We don't see LTE. What we see when we look at ammonia spectra, now it takes a pretty good signal noise, so this is a recent phenomenon where we have a lot of measurements with sufficient signal noise. You see the right outer is brighter than the left outer. You see rho greater than 1, and you see the left inner is greater than the right inner. So typically that's what you see, and it's almost every source shows this anomaly. Right? So ammonia excitation is not LTE. It does not conform to the expectations of LTE. And this effect happens in many, many sources, many types of sources. You have hot sources like the top one here, you see 6334, and you can see the anomaly there. This is a kind of a warm source, an SEA, and you can see the anomaly there. And this is a cold source. That's the phone number, and you can see the anomaly there. Right, so what's astonishing is that across a wide variety of sources, they're not necessarily warm, they're not necessarily hot, they're not necessarily cold. A large variety of sources in various evolutionary phases share this pattern. So here's my favorite sentence: anomalies are ubiquitous. Let's just parse that one for a while. Okay. So how does this all come about? Well, the mechanism that produces this was actually proposed a real bang-up job in 1985. This was Jürgen's thesis. Jürgen is a very smart guy, and he got it kind of right and kind of wrong. So what he found was that in order to make this thing happen, the mechanism requires the linewidths to be very narrow. But the observed linewidths are not very narrow. The observed linewidths are actually quite large. And so what Jürgen proposed, Jürgen Gitter, was that there's a huge number of small cores, and each of those cores was narrow-lined, it had the anomaly, and then the observed linewidth that you see is dispersion among those cores. It's like a swarm of bees. So this is the swarm of bee model. Now, it turns out after 43 years, Jürgen was kind of right and kind of wrong. He had the mechanism right, but the swarm of bees is problematic, and I'll tell you why. So how common are these anomalies? Can improved models help us understand them better? And do they require us to reconsider our concepts about the velocity and spatial structure of larger clouds? And the answer is yes, they do, and I'll explain why. All right, so here's the mechanism in a nutshell. This is the mechanism is radiative trapping. Radiative trapping occurs when you have an optically thick cloud. So let's imagine we have an optically thin cloud. The optically thin cloud has a molecule in the upper state. It makes a transition by spontaneous emission. The photon leaves the cloud because it's optically thin and escapes. There is a net change in the population. You have one fewer molecule in the upper state and one more molecule in the lower state. So when you emit a photon that escapes, you change the population. If, however, you have an optically thick cloud and that photon is emitted, there's another molecule in the cloud that is very likely to reabsorb it. And then there's no net change in the population. You still have one molecule in the upper state and no molecules in the lower state in this toy example. And this is a statistical result. What it means, really, is that it takes longer for molecules, on average, to make that transition. Now, eventually, this photon will escape and it will change, but more molecules stay in the upper state than they would have if the cloud were optically thin. So an optically thick cloud, because those photons are trapped, they stay in the upper state, and it's an effective change of the radiative decay rate. So now we have to modify our transition rates. The radiative decay rate, the spontaneous rate, is now modified by this factor beta, where beta is the escape probability. If the probability of escape is 0, there's no transitions at all downward. If the escape is 1, then you're in the normal state. That's the optically thin state. So the Einstein A coefficient now is modified by this factor beta. And beta is roughly 1 over tau. It depends on geometry. For a slab, it's 1 minus e to the minus tau over tau. For a sphere, it's 1 minus e to the minus 3 tau over 3 tau. But it roughly goes like 1 over tau. This delays the transitions downward. The trapping changes the excitation. All right, so what's the big deal about this? Well, the critical density, and that's the density at which the radiative rate is the same as the collisional rate. That is the boundary between thermal excitation and subthermal excitation. That is proportional to the Einstein A coefficient. If the Einstein A coefficient is now decreased by a factor of beta, increased by a factor of beta, the rate is slower, then the new effective rate is something like the old Einstein A over tau. So the factor of critical density decreases by that factor of beta, or 1 over tau. And so if you have tau greater than 1, the lines are trapped and they're much easier to excite, because radiation is now less important and collisions are more important. So if you make the radiative rate a lot slower, collisions now can compete better with the radiation. So an example that you probably should be familiar with, CO1 to 0. The critical density of CO1 to 0 is about 2,000 particles per cubic centimeter. And yet, we see bright CO1 to 0 emission for densities of about 100 particles per cc. Much, much smaller than the critical density, and you shouldn't see it, but you do because it's trapped. The optical depth of CO is about 20, and so now the effective critical density is no longer 2,000, it's 100, and you can excite CO in low density gas. Any questions on it? This is the crux of the matter. Got it. All right, there'll be a quiz.
So what is the difference between the different hyperfine components? It means that one is radiatively trapped and one isn't.
Yes, that's
You're coming to that.
I'm coming to that. That's a brilliant question. Very, very, very perceptive. And here it is. Okay. Now, look, I'm not going to ask you to memorize that, but what is happening? So the ammonia 1,1 levels are these guys down here. They are fed from above by the ammonia 2,1 levels. And that's the only way you can get population into the radiatively into the 1,1 state, from above. These are far infrared transitions. So this is the 2,1 level. These are the 1,1 levels that it feeds, and there's the hyperfine pattern that we're looking at from the 1,1. So what we in order for this non-LTE thing to work, we have to populate these things in a non-LTE way. So how is that done? So they are fed by these transitions. So if you want to feed the lower levels here in the 1,1 state, they're coming from the upper levels of the 2,1 state. And these transitions are the things that feed population into the 1,1 state. Similarly, if you want to feed the upper levels of the 1,1 state, they're coming from the lower levels. They're coming from the lower levels of the 2,1 state. Now the point here, and this gets to your question, the hyperfine pattern of the 2,1 to 1,1 line is fixed in velocity space. And it's actually quite a narrow pattern. The cluster of lines is bunched up. There's a bunch of lines within about 0.3 kilometers a second or so. And then there are these outer lines, hyperfine lines, that are separated from that inner cluster. That's the key to this mechanism, and I'll show you what happens. When the hyperfine lines overlap, there's extra optical depth. And so when the hyperfine lines overlap, those lines are trapped. When they're isolated, they're not overlapping, there's less optical depth, and they're not as trapped. So the net effect is selective trapping. Some of the hyperfine lines are trapped, and some are not. And that difference then leads to a difference in excitation of the 1-1 state and leads to these hyperfine intensity anomalies. So I'll show you how that works. Here's the 2-to-1 to 1-1 state. These are the lines that are feeding the lower state. And these four guys are bunched together. They're very close. And if it has a thermal line width, this is what the profile looks like. This is effectively proportional to the optical depth. So these guys in here that are overlapping experience a much larger optical depth. They get trapped. And these guys out here are relatively isolated. They experience a smaller optical depth, and they're not as deeply trapped. So this line is the least trapped in blue. This is the 1-0. This line is the next least trapped. That is the 2-to-1. And then the rest of the lines are very trapped because their hyperfine lines overlap and they blend. So now you can see that the excitation is going to be different for the different hyperfine lines because there's different amounts of trapping going on. So let's go back to this level. Here's how they're fed. The blue lines are the ones that are least trapped, and those go very fast. And they drain population very quickly to the bottom state. And so this level is overpopulated, and this level is overpopulated because the blue lines are least trapped. All right, so now you have an overpopulation in this state and overpopulation in this state. Now what happens when you make a transition from this overpopulated state to a less populated state? It's going to be brighter because the excitation temperature is going to be higher because there's more population in this state than LTE would imply. Similarly, this one is going to be fainter because it's going to a state with extra population in the bottom state, and the excitation temperature will be smaller. So now you can see where these hyperfine anomalies come from. This is the bright outer, and that's the line. That's the one that the ROA. That's the top of the ROA.
The pumpkin lines are far infrared.
Correct.
And then the millimeter lines that you'll see in the...
Yeah, these are 1 centimeter ones.
Oh,
Yeah.
1 centimeter.
Yeah, and the same thing happens here. These are the next most trapped, or next least trapped line. And they'll lead to a slight overpopulation. And so the lines that are slightly overpopulated will be brighter if it's in the upper state, and fainter if it's in the lower state. So that's what gives rise to this selective pattern. Now, this all depends on wavelength. Remember, this hyperfine pattern is fixed in velocity space. And so if you have a narrow line, these lines on the outside remain quite isolated. But as you broaden the line, this is only 1 kilometer a second, then they all get blended. And there's no difference really between the optical depth that this line sees and the optical depth that this line sees. And that destroys the mechanism. Right? So once they're all blended and the lines get broad, the selective hyperfine trapping goes away, and you should not see a hyperfine anomaly. So this is a narrow line phenomenon because you need these guys to be isolated, and if the lines get too broad, they're no longer isolated.
Can I ask a
Sure.
short question?
Yeah.
So in stellar atmospheres, line broadening, there's the concept of microturbulence and macroturbulence.
Well, you are really on top of my talk. It'll come up. Yeah, well, you're right. So the difference the question is the difference between microturbulence and macroturbulence. Microturbulence, every cell in the cloud has the same turbulent line. Macroturbulence, there's swirls and the eddies approach the size of the cloud. So they can be locally coherent, but globally incoherent. Okay. So what do the observations say? So I've done 2 surveys, one with the Green Bank telescope, that's called ramps. If you've never had a ramp, they are delicious. They are wild leaks. They are absolutely spectacular. Everyone in Green Bank is eating ramps when it's April is their season. And the whole county smells like ramps, even the people. CAHCMC, this is a terrible acronym. I should have gotten something that at least was a word, but this is a survey that I did with the Australia Telescope Compact Array. This is an interferometer, and I looked at a bunch of targets, about 50 targets. These are dense cores. All right, so we see the anomalies. So this is a map of this particular source, and this is the Rho right outer to left outer. Remember, greater than 1 is an anomaly. And you can see this is anomalous all throughout. I mean, white is not anomalous. This little thing of blue, I don't know what that is, but it's mostly anomalous. Also, Lyrae is also anomalous. It's kind of orangish. And if you plot each point, each pixel, on a plot and draw contours around, so this is Rho versus Lyrae, you see that most of the points lie in this place, to the upper right of the LTE 1-1 point. So clearly, this is not LTE. This is non-LTE. This is very anomalous. And if you look at the interferometer data, you see that any source where we have enough resolution and enough sensitivity, the LTE points marked by this plus sign, almost all the points are anomalous, right? Rho seems to be higher than Lyrae, but most of the points are up to the right, up and to the right. So this is at 3 arcsecond resolution. Now ramps was a single disk survey taken with Green Bank, and this is 32 arcsecond resolution. And it doesn't have the sensitivity, but with a lot of points, you can get a good mean and median. And so this is the kind of typical error bar. These are all the points, and you can see it's also up and to the right. So we have Rho greater than 1 is about 1.2 or so. We have Lyrae greater than 1 is about 1.1 or so. So this is why I say that anomalies are ubiquitous. And if you plot the histogram of all the pixels in the interferometric survey, this is 1, and here's the distribution of pixels. And you can see some of those are really quite anomalous, and these are still well above the noise. So you get the median is around 1.2 and 1.1, but you get some points that are very anomalous. You also get some points that are below 1, which is interesting. Same thing with the ramp survey. The single dish survey gives you a similar result. Again, this is the median of Lyrae is about 1.1 or so. The median Rho is about 1.2. So this is a ubiquitous phenomenon, and it gives you roughly the same hyperfine anomalies on each place. So this is a universal process. There's something going on in every cloud, or most clouds, that give rise to this phenomenon. So this is just the statistics with the mean, with median from the two survey. They agree pretty well. We're getting about 20% anomaly on the right outer and over left outer, and 10% anomaly on the left outer over right. The medians are about the same. The means are a bit different. The interferometer shows more extreme values in both of these quantities. Okay. So that's the summary. 20% anomaly in the outer hyperfines, 10% anomalies on the inner hyperfines. We see them with both single dishes and interferometers. And what was disappointing was there's no correlation between these values and any other property of the gas that I could find. It doesn't depend on temperature. It doesn't depend on column. It doesn't depend on the velocity gradient. There's something, it's not obvious what is going on. So we undertook some new modeling to try to understand what is happening. Now, SW85, Stutzky and Wintervisser, they made some assumptions when they did their pioneering study on this, mostly because computing was really difficult in 1985. And so they made some simplifying assumptions. One is they put a cluster of 4 central lines, they put them all at the same frequency, just to save time. they assume what's called an infinite order sudden collision approximation, which has to do with the ratio of the hyperfine collisional rates. And they used the collisional rates with helium and scaled them to hydrogen. So the new models relaxes these assumptions and achieves more realistic results. So I used the MOLPOP package. This has been around for quite some time, but it has the advantage that it treats overlapping hyperfine lines. And so I put the hyperfine lines at their correct frequencies. I used new collisional rates with hydrogen rather than helium. And this paper abandons this infinite order sudden approximation. Now, look, it broadly confirms what Schlitzky and Vinivesser found long ago. The selective trapping is the right mechanism. We get differences in the details, the exact values, but the broad brush strokes were confirming that mechanism. Yeah. So just to go over this, why they might be different. So Schlitzky and Vinivesser put all four of the central hyperfines at the same frequency, just to save computing. Here's the actual hyperfine spacing, so we use the right spacing. By the way, because of this, if you put them all on the same frequency, you're going to increase the trapping artificially. Now that they're all on top of each other, the optimal depth is much higher for each of these lines, so it will enhance this effect. So we do see the selective trap, and what does that mean? The escape probability for the different lines are going to be different. And so here's the escape probability for these different feeder lines, these arm thread lines. And you can see that they're different. And if beta is different, then so is the excitation temperature, because beta will feed in, the effective critical density is now beta times the original values. So the fact that these curves are different tells you that you do have this selective hyperfine trapping, and that gives you the hyperfine intensity anomalies. We also see the effect that if the lines get too broad, the effect disappears. So in very narrow lines, we have a big difference between the escape probabilities. If the line widths are about 0.8 kilometers a second or so, that difference disappears. They get much closer together. And if you go to like 1 or 2 kilometers a second, there is no difference, and there is no selective traffic. So it destroys the anomaly. And that's kind of the key point of this talk. Now, we can compare our results. What we see is we broadly get the same kind of pattern that Schlitzky and Vinivesser did. They see kind of larger gradients and more sensitivity to temperature, but broadly we get roughly the same pattern. All right, so both sets of models give you the anomaly, rho greater than 1. Both models give you IRyA greater than 1. Over the parameter space, we see the anomaly gets stronger when you increase the column density over the line width and optical depth, the density and the temperature, and it clearly survives this trapping mechanism, selective radiative trapping survives. The differences are that the Schlitzky model is more nonlinear. We get smoother gradients, and that's probably because of this. Putting all the hyperfines right on top of each other enhances the trapping artificially. Okay, so let's show some. So what I'm showing here is N over delta V, essentially optical depth, along this axis, and density along this axis, and the colors tell you how big the anomaly is. It is very easy for MOLPOP to reproduce high values of rho. So in this particular parameter space, this is 30 degrees. At temperature of 30 degrees, at high densities and moderate columns, you get very anomalous spectra. You get kind of moderate spectra, or moderate Leary anomalies. And these dark contours are the means that we get from our surface. So these are the target that we're trying to hit. And by and large, we can hit them. Now this is for quite a narrow line. This is essentially the thermal line, which is the narrowest line you can get. We do see the effect disappear with linewidth as predicted. At narrow lines, the anomalies are strong, and at broader lines, the anomalies go away. So this is the row next to the medians for both surveys. And you can see once you're about bigger than 0.8, you can no longer count for the observed rows. And the same thing with Lyrian. As the line width goes on, lines overlap, they blend, there's no selective trapping anymore, and here's the target, what we observe, and again, it's about 0.6, maybe 0.8, and then it goes away. So this is a narrow line phenomenon. Now we can go up to about 0.8 kilometers a second in line width and still get decent swaths of parameter space that are consistent with the observations. So you can see here, this is the Rolo target, this is what we observe. Here's the Lyrian targets, what we observe. And for kind of reasonable, like highish densities and moderate columns, we can reproduce the results. Now, so this is somewhat of a success. We can reproduce the results with this kind of swath of parameter space. When we have temperatures in about 40, 50 Kelvin, we have densities of about 10 to the 4 or so. When we have this column density, and when we have this line width, we can reproduce the observed results. But the mechanism requires 0.8. Once you're above 0.8, the lines blend, the selective trapping goes away, and we should not see an anomaly. So what do the observations say? Well, it doesn't work. Because the line widths that we observe, here's their maximum line width for the anomalies to survive, and here's the measured line widths, and all of these show anomalies. Right? So now we have a conundrum. It's even worse for the CAHCMC data, the interferometric data. Those line widths are even bigger. They have to be smaller than this. None of them are smaller than that, and yet they all show anomalies. So here's the puzzle. How can you have a mechanism that requires narrow line widths, but you observe broad lines? So there has to be something in the structure of clouds, the velocity structure or the physical structure of clouds, that allows you to have simultaneously narrow radiative line widths, but broad global line widths. So how do we get around this? Suppose we have a bunch of entities, call them bees, call them cells, that have narrow line widths, and they talk to each other radiatively only. They talk only among themselves. Each of those cells, or bee, will have an anomaly, and then you have a velocity dispersion among those cells, but the cells don't talk to each other radiatively. The lines don't overlap, or the radiation from one doesn't pass through the other, or is shifted out of resonance. That works, that's fine. But then the problem is, how do you prevent them from talking to each other? Right? So each cell has a narrow line, produces the anomaly just fine, but now somehow the ensemble has to be broad without talking to its neighbors, radiatively. So there are two ways to do it. One is you have a swarm of bees. Each bee produces an anomaly, but they don't overlap spatially, and so the radiation from one bee never passes through the radiation through another bee, and therefore they're radiatively distinct. So if you think about this, you have a swarm of bees, and the filling factor, the aerial filling factor of each bee is small enough so that it doesn't overlap another bee. So that's one way to do it, and that's what Jürgen Stutzky proposed. Another way to do it is to not worry about the spatial overlap, worry about the velocity overlap. Suppose you have a bunch of blobby clouds, but this cloud is at a different velocity than this cloud, and this cloud is at a different velocity than this cloud. In other words, you have a gradient in velocity. Then the radiation from this cloud can pass through these two without seeing them because they don't overlap. They're not in resonance. These clouds are sufficiently different velocities so that the radiation from this cloud passes right through without interacting. And that's a way you can do it. It's not space in spectrum. This is a spectral separation of the clamps. So, Guy, do you understand the two distinctions?
So that requires the spatial scale of the velocity gradient to be large compared with the weekly path of the computations.
Something like that. Yeah, Enrique and I were debating about what's the exact criteria for the velocity gradient. I think we're landing on the same place on that. So yeah, and whether this velocity gradient comes about from turbulence or flows, I don't care how many targets are, but it just has to be a large enough gradient to keep them spectrally separate.
So
Yeah.
these kind of blobs or entities or
Yeah.
whatever you call it, are part of your single core that you are looking at.
Yes, correct. Yes. So this is substructure within
Some structure that you don't
within the
distinguish you don't see that substructure.
So this is one of the, so I'll give away one of the punchlines. The swarm of bees, we should see them with interferometers. We would see bees that are that dense, and we don't. So I think this model's gone. I think we're now back, we're back to something like this.
But what has to be the difference in velocity?
They have to be such that it's out of resonance, so the velocity gradient is bigger than the internal line width.
Which is?
Don't know. That's why we have an excellent modeler and simulator in our midst, and that's why I'm in Moreau. So yeah, but I can give you the numbers that are required, but it's they're not crazy gradients. Anyway, let's talk about the swarm of bees model. So this is the idea that actually this is a poor representation because you should be able to see the gaps between the bees. So this is a little too volume filling. But in any case, what you have is each core has a narrow line width, produces an anomaly, and then you have hundreds of cores that produce the observed spectrum. And what you see as the observed line width is the velocity dispersion among the bees, among the swarm of bees. The problem with this model is shot noise. If you have a bunch of identical bees and you want them to sum together to make a spectrum, then if you have only a few bees, you only see a few spikes. Each bee produces a spike. And if that number is small, the spectrum should be very spiky. So if you have only 10 or 30 or even 100, you should see individual bees at different velocities. The real spectrum is actually very smooth, something like this or this. And just the smoothness of the spectrum alone means you have a large number of bees. Otherwise, you would see this spiky spectrum. So as you drive yourself to more and more bees, each bee has to be smaller and smaller. And now you're starting to get down size scales of 100 to 30,000 AU. I don't know what that is. That's a solar system. So the size scale that you get is something like, maybe 1,000 AU, maybe 6,000 AU. And we would see these things with interferometers. If we had things of this size and that column density, you should see them with ALMA, or you should see them with VLA. And really sensitive searches for very small scale structure doesn't find these things. So the other problem is if you get more and more bees, they become very dense. And if they become too dense, then the anomaly goes away because collisions dominate and there's no radiation doesn't matter at all. And so you don't get the mechanism. So I will say it's increasing. My personal opinion, this is dead. This model is dead. But I will be scientifically accurate and say it's increasingly difficult. All right. So the other possibility is a large velocity gradient. And there are two possibilities here. It can be turbulence. So turbulence can provide velocity gradients, or it can be flows. You can have gravity pulling things around. You can have flows that provide these velocity gradients and pull each cell out of resonance with the one behind it. And both could be at play. So the problem here is how do you pack hundreds or thousands of these things into the volume. So I'm going to look at turbulence because I could do that quickly on my laptop, but it doesn't have to be turbulence, it could be flows. So there are two ideas floating there about turbulence, and this gets to your question. There's microturbulence, where every cell the eddies are smaller than the mean free path. So every chunk of cloud has the same line width, the same turbulent line width. And this is actually a common, I think, misconception of molecular clouds that astronomers have, that turbulence provides a uniform pressure everywhere, and because the line widths are the same everywhere, and you just replace the sound speed with turbulent dispersion, and away you go. Another type of turbulence, when the turbulent eddy size is bigger than the mean free path, that's macroturbulence. And then you have like individual zones that are in motion with respect to each other. So this is a cartoon sketch of those two different things. So the way to think of macroturbulence, and this is from Enrique's book, is that on small scales, the line widths are small, and on large scales, the line widths are large, or the velocity differences are large. And that could do this, right? Because narrow lines on small scale would produce the anomaly, and then the velocity difference on large scales will pull them out of resonance, but you would observe the sum of all those, and you would get a broad global line width, which is just the sum of all those individual cells. All right, so what line width does a cell see as the photons traverse the cloud? In microturbulence, they would all see the same line width. And in macroturbulence, the velocity fields are correlated. Nearby cells share the same, tend to share the same velocity, and distant cells have different velocities and may well be shifted out of resonance. So macroturbulence is a possibility for this phenomenon because it produces narrow radiative interacting line widths delta B rad than microturbulence does. So I did a toy model. This is the toyest of models, right? So I just said, okay, I'm going to take a Berger's turbulence. This is a compressible turbulent velocity field, and you can see that you don't get big spikes. The velocities tend to stay near each other. So the velocities are correlated. If you're at this position, the velocity near it is likely to be the same. But overall, over the whole cloud, there are big excursions on large scales. And so locally, so say you're a photon here, you see a bunch of nearby velocities, that's a narrow line. But then that narrow line can pass right through this piece of the cloud because it's at a totally different velocity and it's not in resonance. It won't absorb the photon at the same velocity. And here's the density field. I chose a large normal density field because that's what it tells me is right. And so then I just did a simulation. What ammonia spectra would I see in this toy turbulent model? And here's the answer. There's a big difference between microturbulence and macroturbulence. This is you're integrating from a cell through the cloud, and this is how many cells you integrate through. After you get to about 8 cells in the microturbulent model, the global line width is already high here. And that's because each cell has the same line width. And so if you start averaging cells together, they will have the global line width. In the macroturbulent model, however, because they're correlated, nearby cells see the same velocity, and it's only when you start integrating over large numbers of cells, a large piece of cloud, that the global line width grows. So in the end, you want to reach this target, say 2 kilometers a second. Microturbulence does it too quickly because every cell has a big line width. Macroturbulence can remain narrow line locally and broad line globally. So that's an idea that at least is plausible that could account for the hyperfine anomalies where you need local line widths to make the anomaly, but you need to observe a broader line width global. Does that make sense?
Yeah.
You mean about 1,000 cells more or less? Yeah.
Yeah. So, again, so one of the reasons I'm here is that I'm almost embarrassed to show this. I want a real model of a real cloud and then run the radiative transfer through that real cloud. But this is just a plausibility argument. Okay, so here's the spectrum that comes out of my toy model. And so this is something like the radiative line width here. The full width half max of the central peak is about 0.8 kilometers a second, which is what you need, right? The local line width is 0.2 kilometers a second everywhere. So the turbulence broadens that local line width to about 0.8 kilometers a second, and then the observed line width is about 2 kilometers a second. So it kind of works. And when you do the radiative transfer of that and run the MOLPOP models at each point, you preserve the anomalies. So this is the hyperfine anomaly that you observe through my toy cloud, and you can see that it is indeed anomalous. It preserves the anomaly, even though the measured line width is something like 2 kilometers a second. The intrinsic line width is about 0.8 kilometers a second. The irradiated line width is small, the global line width is low. So this is preserving the anomaly, so it shows that it can work. On the other hand, if I did a microturbulent model, the anomaly disappears because it's always 2 kilometers a second, and when the lines are hopelessly blended at 2 kilometers a second, there's no longer selective trapping, and there's no longer hyperfine anomalies.
Doesn't it still suffer from the smoothness problem?
I'm sorry?
Doesn't it still suffer from the smoothness problem?
It does still suffer from the smoothness problem, yeah. Well, it actually does, because the smoothness problem is it's assuming n-identical beads. I'm no longer assuming n-identical beads.
But you also have a lot of structure in your individual.
Oh, I do, yeah.
Components.
Yeah. So
you say that
that's why with a beautiful real cloud and many, many more pixels,
Okay.
I'm hoping those little spikes go away.
Okay.
Yeah. I think this is a limitation of my toy model rather than a limitation in the idea. All right, so all models show that narrow line widths are required to generate the HIAs, but the observed line widths are much broader than the models require. So to preserve the narrow local line widths, we require velocity gradients. We require shifting the narrow line regions out of resonance. So macroturbulence is a promising possibility to produce these HIAs with a narrow radiated line width but a broader observed line width. Now, another possibility is that we should listen to Enrique and say forget about turbulence, it's all flows, it's all gravitational motions. And that could also do it. I'm not sure it will, but it could also do it because what you need is just a big enough velocity gradients to pull the cells out of resonance with each other. Okay, so to conclude, ammonia 1,1 hyperfine anomalies are ubiquitous. The surveys show ROAs of 1.2 and layers of 1.1. The LTE value would be 1, so it's clearly not in LTE. The interferometer shows slightly bigger values and more dispersion than the single dish values. The new MOLPOP models with modern collisional rates can reproduce the hyperfine anomalies via the selective trapping mechanism, but will require the local line widths to be narrower than observed. So you need somehow radiative decoupling of the narrow line spatial or spectral elements. The swarm bead model is essentially ruled out because we should start seeing the beads with interferometers. So the simple correlated turbulent toy models seem to reproduce the anomalies, and that is one way that we could explain this global phenomenon. So the takeaway message is that these hyperfine anomalies rule out a simple microturbulent description of molecular clouds. So you can't think of turbulence as having a pressure, the same pressure everywhere. But instead, you need velocity coherent structures embedded with broader turbulent and large scale bulk flows. So thank you for your attention. I'm happy to take some questions.
Questions?
Are you able to detect these velocity gradients or whatever they are?
So these would be gradients along the line of sight, not across the line of sight. I do see spatial gradients in the sense, this voxel A has a slightly different velocity than voxel B. And I was praying that the anomalies would be stronger at these across the line side, the tangential velocity gradients. I didn't find that. So the problem is it's along the line of sight, not across it, and you just can't measure that.
Laurent?
So does this have a negative effect on using ammonia as a thermometer?
Slightly, yes. So what people tend to do in the presence of these anomalies, they average the outers, they average the inners, and then they use it as if there were no anomaly. That's okay. You get errors. Now, what the biggest problem is, if you use that for optical depth estimates, they can be off by as much as a factor of 10. So the optical depths are underestimated by that factor of 10 for some of these extreme anomaly cases. Yeah, I've done that work. The temperatures are not bad, but you can make 20-30% errors in the temperature if you don't take into account the anomalies. But where you really suffer is the optical depth estimates.
So if the single dish mappings show lower anomalies, so that would be consistent with this preference for the macroturbulence, because with a big dish, with a single dish, you start
You're averaging
to see
yes. Yeah, that's a good point. So what it says is what's happening on small scales is somehow being washed out in the single dish measurements. But they get the same medians. But the dispersion is larger at small scales than it is at the large scale. So there is some averaging going on. I would agree with that. Haven't looked deeply into that, but I think that makes a lot of sense.
So if one makes a, say, like a interferometric survey of pre versus protostellar cores with narrow versus wide line widths, do you expect then that in a subsample you would have like a maximum effect?
So
whereas the others would be like consistent with LTE at high enough angular resolution?
yeah, so our survey is about 3 or 4x second resolution, and we did include some cold cores along with our warm cores or clumps. I guess these are technically clumps. We didn't see any real difference in the strength of the anomaly between cold, warm, or hot.
But maybe because of the resolution, no?
Maybe because of the resolution, yeah. So, that's kind of early days. We have 50 sources in our survey with good signal noise. The problem with this sort of work is you really need excellent signal noise, because you're looking at a 10% difference in intensity. That's, you got to integrate for hours to get enough signal noise. But it is plausible that we see that. I was expecting to see more anomalies for narrow line sources, and I don't see that. The anomaly strength seems to be independent of the line width, which is telling me it's not the global line width isn't producing the mechanism. Something on smaller scale is producing it.
So returning a bit to what Luis Felipe was asking, have you looked at the second order structure function of the velocity fluctuations on the plane of the sky? Because that could give you information about what the spatial scale, the correlation length, the velocities.
So I've looked at radius, I've looked at velocity gradients. I haven't really done a deep comparison with the second moment, but that would be
not the second moment, but the structure function of the velocity centroids,
Yes.
how they vary on the plane of the sky.
I haven't done that. That's a good thing to do. I would agree with that. So the structure function, there may be information in the structure function that somehow.
I mean, it's very complicated to interpret because you've got the projection effects, but you assume it's isotropic and a certain power law, and you can work out more or less what the correlation length is.
Right. That's so to get a correlation in length. Yeah. That's a great idea. My friend and I are going to do that.
Our students.
One of you will have that lovely chance.
Any more questions? On Zoom, we don't have any? No? Well, Alberto, again.
What about the positions with the inverse, with the ratios lower than 1?
With the redshift or
with the line ratios, the
yeah.
inverse anomaly.
Yes, I haven't really looked hard at those. So we only see those within. I mean, the ones that we see less than one with the single dish. That's all just noise, right? There's no real anomalies, inverse anomalies. For the interferometer, yes, we're definitely seeing some positions where the anomaly is smaller than one rather than greater than one. Now our models can kind of produce that in some situations. So it's not a terrible surprise to me that if you're if you're up to the upper right on this n versus column density versus column plot, that's where the biggest anomalies occur. But if you're down here where both are small, then you can get inverse anomalies from our models. So I think it's certainly allowed by the models. I haven't looked deeply into whether those things have different physical parameters, but it would definitely be worth looking at.
Okay, no more questions. Well, we thank Jim again.